Hello everyone, this is Sean, and today we are moving on to design, like it says. Now, for the last 6 chapters or so, you guys have been working on analyzing the problem, taking real-world problems and trying to convert them using the charts and the diagrams that we've been making you use to convert them into some cohesive plan that we are then going to now try and convert into the design approach to a program. So design, unlike analysis, is now focusing on building the system, on creating a blueprint for good, efficient code that we are then going to actually implement to make the program. So what we're going to do with design is we're going to figure out how the data is used, where it's stored, how we're going to group all these different classes and things together that we've been building and diagramming in the analysis section. How we are going to interface and use the system, specifically what kind of physical architecture, like are we going to be using a phone, are we going to be using a laptop, a desktop. They're going to have different input mechanisms that we normally rely on. And these decisions are what we are going to be focusing on now in the design portion of the task of our big system analysis and design course. So analysis and design are, as it says, highly interrelated. You are going to go back and forth. You're going to do your analysis, then you'll start working on design, and when you work on design, you're going to realize, oh, I need to add that class back in because I need it for this. And so then you'll go back and redo your part of your analysis, and then that's going to then affect other parts of your design. So these things are not mutually exclusive. You don't just do one and then, oh, that's done, it's set in stone, and I can never change it, and then I'm going to go on to my design. No, they're working together throughout this whole planning phase of your program. So with that said, let's talk a little bit about the design process. Now, there are going to be 4 basic steps that we're going to use. We're going to be verifying and validating the analysis models. This is something that we've talked about for the last several chapters. At the end of each diagram or each chart that we had you create, we said validate it, go back over it, look at it, make sure everything is in there, make sure all the information is correct and you don't have extraneous information. So that is the first part of the design process, is once you've got everything in place, go back over all the analysis models that you've created. Now, these analysis models, there were 3 basic ones that we've talked about. We've got the structural, the functional, and the behavioral models. And each one of them are connected, and so you need to make sure that everything is sane. We like to call it the sanity check. Make sure that all of the objects and classes in one model actually relates to something in the other model. If there's something, an object or a message or an activity in a model that doesn't exist in the other models, then either it needs to be removed or you need to add it into the other 2 models. That's where the verify and validate comes in. Once that's done, then we start converting the analysis models or grouping them, depending on how you looked at it, into design models. And we'll talk about that a little bit. And then creating packages and package diagrams is further grouping things together into similar objects or similar classes that are either working together or they're the same kind of class or object. And then finally, decide upon the design strategy. And we're not going to touch on that too much. That'll be left for a little bit later. But for now, let's talk about verifying and validating the analysis models. So mostly we need to figure out with this, and this is what we've been doing for the last several chapters, do these models that we created, do they accurately reflect the problem that we're trying to solve? The problem we're trying to solve could be anything, right? Whatever the program is attempting to do. Are you creating a scheduling program? Well, if so, do the models that you create, do they all accurately represent the problems that we're trying to solve? We're trying to figure out what the college course schedule is going to be. Well, are all our models working towards that goal? Do we have models representing each of the classes and the students and the teachers and all the other variables that we need? That kind of thing. So test those models. Make sure that those are working properly, that we're not missing anything or we don't have too much extra information. And that's what balance comes in. So balancing, they have in the slides here some bullet points for the different kinds of balancing for the different models. It really comes down to, do you have the same information in each model. So in this case, like for functional and structural models, a class in the class diagram needs to have a use case that it's related to. If it doesn't, then why is the class even there? If you have a landlord class, but there is no one renting any apartments, then why do you have that landlord class, right? If your use cases don't actually support having these classes, then you don't need them. On the other hand, if you have a use case that has a landlord that you've got someone renting apartments from, some people are renting apartments, when you don't have a landlord showing up in your class diagram, well, now you should be adding a landlord class because they are part of the big problem domain that we are working with, right? And that works for activities and operations in the class diagram and so on and so forth. For the most part, again, make sure that everything that is in one of your diagrams and one of your models, is in the other two models, and that they make sense, that they are what we call, again, the sanity check. So again, functional behavior models, same idea. Make sure that they're associated. The sequence and communication diagrams need to be associated with a use case. If they're not, then that communication does not occur because the use cases are what we are trying to do, right? The use cases are modeling what is happening in our problem. And if you don't have a particular communication occurring in any of your use cases, then you don't need that communication in your program, right? So an example of that would be if you've got a method that checks the age of a person object, but that never happens in the problem that you're trying to solve. No one cares about the age of anybody in your problem. Well, then you don't need to get their age. You don't even need to store their age probably. And so that's the kind of thing you're looking for when you're balancing these. And then the last one, structural and behavioral models, same idea. You're just basically making sure that everything is agreeing with everything else. So once you have balanced, we need to then start moving these models, converting them, evolving them into the design model. Now, the design model is going to include the non-functional requirements. Analysis models, everything we've done up to this point has been just focusing on getting the problem solved, accomplishing whatever it is that this program, that this system needs to do. So we have not worried about any of the non-functional requirements, even though we had mentioned what non-functional requirements were back in chapter 2 or 3. So non-functional requirements would be things like performance. So say we have an e-commerce system, and functional requirements were that we need to be able to process a user purchase through our e-commerce system. But a non-functional requirement might be we need to process 100 purchases in an hour with this system, using this system, right? So that's the kind of difference between functional and non-functional. You're going to have non-functional requirements in the design model because you're taking those into account. The analysis model has given you all the information that you need to solve the problem, but now how are you designing this system to solve that problem? Are you designing it to be efficient? Are you designing it to just function barely? Are you designing it to work on a very low-powered system? Are you designing it to work like on Amazon where they have it clustered across a number of servers? So this is the kind of thing that you need to take into account in the design phase. And we're going to talk about some of these specifically next couple lectures. I think Chapter 9 focuses on the data and how we would be storing and retrieving and working with the data. And Chapter 10 is human-computer interaction. So what does the interface look like? What kind of interface are you generating? And things like that. So this is the kind of stuff the questions that you're going to answer with design models. And I'll just mention also, because it is on the slide and it's important, is that the system needs to be maintainable and affordable. Efficient and effective is good, but really maintainable and affordable is key. Specifically affordable because money is finite, and that is just the way it is. So everything that you design needs to be able to be run after it's been designed and implemented. It needs to be affordable. You can't have a system that will constantly need a lot of work and will constantly need money sunk into it. And so the design will take into account things like that. And then to do this, we're going to use certain kinds of steps that will group and organize classes, allow us to separate things out and partition things into cohesive groups. that will help us then figure out what's talking with what and how best to go about designing the system at large. So let's talk about those. These terms that you see, factoring, partitions, and collaborations, and layers, you know how to do this. You just may not know what the term is. So factoring is basically similar stuff grouped with similar stuff. It can be simple inheritance, like a zebra is an animal, right? So the generic animal class has a child zebra that inherits some basic information from the animal class. It could be constituent parts. It could be like a car class has 4 wheels, and so there's 4 wheel objects inside the car class, or things like that. So we're grouping these things together. That's what factoring is talking about. Finding similarities and differences, and then grouping the similar ones together. And also just other forms of polymorphism, such as abstraction and refinement, which is basically having parents and children. Abstraction is creating a higher level abstract person class for the student class that you're working with. Refinement would be taking the student class and refining it to be college student versus high school student versus grade school student or whatever. That kind of thing. They're still grouped together, right? You're refining these classes or abstracting these classes, but those are still all the same kind of class, with the same kind of job inside this whole system. Partition and collaboration is, instead of grouping them by how similar they are or whether they are part of another item or something like that, this is grouping them by how they interact with each other, how much they rely on each other. An example of that would be a doctor's appointment, where the patient and the doctor's appointment are pretty tightly interwoven. They're both necessary for each other, but they're not really the same kind of thing. One is a person class that is a patient, and one is some sort of appointment class, however you define it. But they rely on each other. They need each other. The patient needs to make an appointment. The appointment needs a patient to be made. And so you would group those together in some partition, saying, okay, this over here, this is the patient and appointment partition, and everything that has to do with the patient and the appointment get sent over there, right? What really happens is this allows us to put things into groups that logically will have one piece of information either leaving or coming in. So in other words, you will have maybe the patient and the patient appointment will be having the same kind of interaction with the doctor or the doctor's office or something. And so keeping them together, you have basically one kind of message that will be passing between those two entities. But you don't need a lot of things. But between the two of them, you need a lot of message passing. And so you keep them in the same group. This is where we start getting into packages, which I'll explain in a second. And I like to think of it as Java, for example, uses packages to group together similar or related classes. With C# and C++, I believe they use namespaces for the same idea. You've got this area that's got all of these different classes or objects or what have you. These are all in the same namespace so that they have different levels of access between the individual classes because they're going to be talking to each other more often. Where when you're in a different package or a different namespace, you can only get access essentially through public methods, right? As opposed to being able to use protected methods or what have you, again, depending on how you've got it set up within the packages. And so the last thing they talk about is layers. Now, layers we're going to go into a lot more detail when we get a couple chapters in, because layers are really how you are accessing and storing the data and the information and the system itself. But for the most part, we group them into areas that represent different elements, different ways that we are building stuff. The best way I like to explain this is we have foundation layers, which is essentially a class that stores and calls other classes. It stores concrete instances of objects, and we'll call other classes to do things and solve problems. The best example of that would be the main class. Java uses that a lot, has a main class and then or a driver class, if you want to call it that, and it's going to be calling all the other classes and creating instances of all that information and then working like that. The problem domain is the stuff that you guys have been working on. These are the objects and the classes that are modeling all of the real world items and people and problems and information. And then the data management layer would be where and how this data is all stored. Specifically, for example, would be a SQL database, or whether it's that or whether it's just some flat file that's storing data or whatever, and how it gets retrieved. That would be a different layer. The user interface layer is completely separate, right? The user interface layer really doesn't need to know what goes on in any of the other layers. It just needs to get the information. It just needs to be told either what to display, or it needs to send the information, the input information from the user back into the problem domain, right? So it's a separate layer, and so it has a whole different group of classes and a whole different function. And then the physical architecture itself. What kind is this a device? Is this a handheld device like a phone or a tablet? Is this a computer? And you're going to have different classes that will be used specifically to handle that issue, those problems, right? So that's what layers are for. Now packages are really closely related to partitions and collaborations. Packages, like I was mentioning before, are where you take similar components, similar classes, in this case use cases, class diagrams, things like that. You put them together. Now, in the design phase, we are specifically looking at the use case diagrams, use cases, class diagrams. We are trying to take our analysis models that we have, those diagrams, and use them to help generate and determine what the design is going to be. And so we package up all the use cases and class diagrams and so on, and all the diagrams, activity diagrams, communication diagrams, things that are the same. And we put them into packages that will say this is the, I don't know, if this is a video game, this is the player character package, and all the information that player character has goes in that package. This is the NPC or monster package, and all that information gets put in there. This is the AI package, and all things related to artificial intelligence get put in there. Things like that. We're basically packaging up all of our models and putting them in groups where it makes sense, where they're related, where they're going to have similar kinds of input and output happening. And really, what we are trying to do is say that these packages represent a broad overall scheme or problem-solving device. And there are times where these packages end up depending on each other. So, for example, in my previous example, the monster NPC package is going to rely on the AI package. The AI package is going to make decisions, and depending on the decisions it makes, it might alter either the state of one of the NPC or monster class, or it may alter the way the communications that it sends to other parts of the system. So it's possible that they can relate to each other or even depend on each other. So very briefly, and we'll get some example of the package diagram, and I'll talk about how we go about creating them in a second. You basically, package is just this abstract thing that we say puts other stuff together. We take other charts and things, and we say this is all under this package. Logical grouping of UML elements, okay, is the way they define it. And that's it. That's what a package is. And the package is entirely up to you, depending on what logical grouping you want to create. The dependency relationship, be careful of, because it's a dotted line with an arrow. The arrow does not point to any message being passed or anything like that. It's pointing to what this package is dependent on. And I'll give you an example here in the next slide where we have a sample package diagram. You can see these are just the different layers that we were talking about. These different 5 layers all have specific tasks involved in the system. If you look at the HCI, human computer interaction layer, it's dependent on the problem domain, the physical architecture, and the foundation. And this makes sense, right? Because physical architecture, for example, the HCI, how you interact, well, if it's a phone, you have a touch screen and you're going to be interacting that way. If it's a computer, you've got keyboard and mouse, and you'll be interacting that way. Things like that. If it's a watch, if it's a smartwatch, it may be voice activated, and that's how you're going to interact. So the HCI is dependent on the physical architecture and how that's put together for what it's going to do. It's also dependent on the foundation, because the foundation is what's going to instantiate this HCI in the first place. Foundation, like I was saying before, is basically where everything is created and how it all interacts. Think of the main class again. And the problem domain, depending on what you're trying to solve or what you're trying to do, the actual output, the HCI, is going to look different. If it's a game, if it's a video game, it's going to look one way. If it's a spreadsheet, it's going to look another way. And HCI is dependent on that problem domain for what it's going to display and what it's going to take as input. So that's how these package diagrams work. So when you see the arrows are saying this package is dependent on these packages for its behavior and for its appearance. So basic guidelines, some of it's common sense. You want to logically organize them into groups that you think are going to best function together. You want to worry about the dependency relationships, but at the same time, this is largely so you can organize different groups of classes, different items in your system that are going to be relating to other items in the same way, if that makes sense. For use case package diagrams, if you are going to be packaging up whole use cases, you need to keep the actors the same because they are the root of those use cases. And finally, use simple but descriptive names for each package. Do not, for example, just call it package A. That's not going to help anybody. Call it, for example, utilities. If you've got a bunch of classes that do little things to everything else in the system, put it in the utilities package. Like I was saying before, have an AI package where all the AI information for your video game goes. It's short, it's descriptive, right? I can look at the AI and say, okay, if I'm looking for a collision detection, I'm going to look in AI. I know that already, right? So I don't have to start searching through package A through C to figure out where my collision detection is. And make them cohesive. So make them make sense. That's what that means. Make them understandable. Make it so you can look at the package, look at the stuff inside and say, okay, I see how all that relates to each other. Not very detailed, I know, maybe not even all that helpful, but that's how you would go about building package diagrams. So when you actually go through and build it physically, set the context like you do everything else. Put a bunch of classes together based on whichever relationship you're worried about. Then create packages from those groups that you've thrown together. Those groups, you're not actually going to put those in the package diagram. The only thing you're going to be putting in the diagram are the packages themselves. So all of this stuff, the first 4 steps, that's just you looking at all of your other classes, all of your other diagrams, and clustering them together yourself, whether it's on another piece of paper or something, whatever. But when you create the diagram, you're only including the packages and the dependencies that you identify. And then, just like everything else, verify and validate those packages. So now, we're going to go to something completely different. What we've been talking about up until now has been what we're going to do, how we're going to get our analysis into design and the different things that we have to think about, specifically the inheritances, the relationships, and and the packaging and things like that. Design strategies, this is more how are we going to actually go and do this, right? But everything else to this point has been we've got a problem and this is the way we're going to solve it. Now we've gotten that. We're done. We know what the problem is. We've identified all the things that this system needs to do. And now we have to figure out how are we actually going to do it. And so the book has 3 basic, it will be 4, you'll see what I mean in a second, but 3 basic strategies for what do you do now that you've got this problem, you've got it analyzed, you know everything that needs to get done. Well, let's actually do this. How are we going to do it? So there are 3 things it says. It says custom development, purchasing packaged software, or hiring an external vendor. Now we're going to go over the pros and cons of each of these. They're pretty self-explanatory. Custom means you do it yourself. Purchasing means you buy it from someone that's already done it. Or an external vendor means you hire someone else to take care of this problem for you. Whether it's they're going to do what you do, they're going to develop it themselves, or they're going to find some packaged software. It doesn't matter. It's not your problem. You have told them to take care of it and thrown money at them to do it. So pros and cons of these, and we'll be brief because they're going to be pretty common sense. So custom development. Custom development is the most specialized. Custom development means you can specifically target a very unique way of solving a problem. You can have it format exactly to the workflow that's in whatever business that you're working for. It's much easier to change things in and out because you're doing it all yourself. You can decide what goes in and what doesn't. And this is an underrated pro for this, but it builds personnel skills. If you start building a system, you're going to get really good at that system, and you're going to get really good at building other systems because you've already built this one. So there's a lot of pros, a lot of positive things that come out of custom development. However, the two cons that are listed here, they're pretty big. It can excessively burden the IT staff. The IT staff being the people that are helping the users all day long. And if you have a custom app, most likely the documentation is whatever you've written for it, which means the IT staff has to learn the program from scratch. They have to go through all the bugs. They have to figure out how to integrate this custom app with all the other things in the workflow of the users. And it's a lot of work. Custom apps are difficult to maintain and to support if you are IT staff. So that's a huge trade-off because that's a lot of money and it's a lot of time for the company. The other is it may add significant risk. Most developers are not security specialists. Most developers are people that want to solve problems. And so they're good at programming and they figure out how to solve problems. But you have very serious security risks that can happen, especially if you open things up to the internet in any way, shape, or form. And also there's a chance that this whole thing might fail, that you might get halfway through and realize, yeah, we can't do this. Either we don't have the expertise or what we're being asked to do is not feasible or any number of problems. And then all the money that was sunk into the project is gone, right? So this is a big problem. And there's also time things they didn't mention is it takes a lot of time. Custom developing your own software is a serious time commitment, time and money commitment. And so you have to make sure that this is going to be a good choice for you if you decide to custom develop once you have analyzed and determined what your problems are and what you need to solve. So the second thing we had was package software. This doesn't have to be commercial. You can have open source package software. It can be free. It can be shareware. Well, not shareware. But it can be open source. It can be certain kinds of, like the GPL, different kinds of licenses that allow you to use it as long as you don't alter, or if you do alter that you give credit or whatever. There's many, many different licenses, but you don't always have to pay. Now, that said, much of the software that's already been written, if it's pay software, if it's commercial software, it's already very efficient. It's already been tested. It's already accepted good software in general. Not always, but usually. And so packaged software is just so much easier because all of the concerns and issues and the troubleshooting are gone. You still have to work it into your workflow, which is a problem because sometimes you have to change the way the firm does business, like it says here. But for the most part, you're saving yourself a lot of trouble. You're paying for it because you're buying the software, but it ends up being a lot easier in a lot of senses. Now, the downsides outside of you may have to change the workflow is you have to accept whatever it is they give you. If you need more functionality than it has, it's not going to help you. It's only going to do what it says. When you buy it for what it does. And then also, because, and this is related to that, is you may have to customize it. You may have to find workarounds for the reason, maybe because Word doesn't type simultaneously in 4 languages like you need it to do. You have to figure out how to make it type in 4 languages simultaneously. Maybe that's going to be part of the internal development or something. So packaged software is good, but it's not always a perfect fit. And so it's sometimes shaving off that square peg to fit in the round hole, if you will. Which brings me to where I'm saying there are 4 different approaches. There is the fourth approach, which is a hybrid approach, packaged software and custom software. And they're calling it system integration. That's where you have some packages, you have some form of some software, and maybe even some old software, and you're trying to update it or create something new. And you bundle it all together and you integrate it together. So this is actually probably the most common way to handle these kinds of systems. that I've seen is that there's some pre-existing, usually commercial, but sometimes open source software, and the developers are creating packages or add-ons or components that work with that existing software to create a new piece of software. Sometimes it's just upgrading. Sometimes it's taking old legacy software that is out of date and bringing it up to speed to work with modern software. Sometimes it's taking some software, but then taking the output of that software and changing it to work with whatever workflow you have, right? This is, I think, from my experience, the most common type of system that people work on. The key challenge with this, though, is integrating it, is getting it to all work together, because they weren't designed to work together. So very often you need to do two things, one of two things. You need to write the data in the same form that the old stuff is in, if you're doing legacy, or just in the same format that the package that you purchased is in. Or you do what we call wrappers. Object wrappers, and this happens a lot, and I think this is probably the way most people solve these kinds of problems, is an object wrapper. Basically, it creates an interface between the system, the old system, or the package system, whatever you want to call it, and the other system, whether it's your custom system or a new system, or whatever those two systems are, the two different systems. And it's a bridge. It's a way to take the data from one and send it to the other, and then take messages from them and send them, basically translating them to match the other system. That's why it's called a wrapper. You can think of this big, basically a wrapper. Picture it like as a big plastic bag that wraps around the old system, and then every time something passes through that plastic bag, it gets converted from the whatever system it was into the legacy system or the other system. An example, I keep on saying legacy or other, but an example would be if you have an old Windows 95 program, and it's old. It's still 16-bit, and it doesn't recognize a lot of modern features. Well, but you still need it because it's got this one thing that it does really well, and you don't want to have to redo that. So you write a wrapper class, and that wrapper class will take data from the new system, like say Word 95 instead of Word 2013. You take a Word 2013 document, you put it through the wrapper, and then or the converter, and the wrapper will then take all of that, and then to the best of its ability, take the information that the old Windows 95 program will need and convert it to that same data format, and then give it to that program. That program will do its thing. It'll send it back out to the wrapper. The wrapper will then convert it back to the new program and send it out, and then give it to the new program, and the new program now has it in the format that it likes. So both of these packages will have their own format and their own way of dealing with things, and then the wrapper is kind of the bridge that allows the two of them to communicate. Does that make sense? I hope so, because it is an important and generally really useful way of dealing with system integration. And system integration is going to be something that you, like I said before, you are going to find and you are going to deal with. But it is often a good approach when you either can't afford or don't really want to do a custom installation, but the existing packages, the existing software that is there isn't really doing exactly what you need it to do. So the last thing on their list was outsourcing. Now, outsourcing essentially is letting another firm come in and help fix the problem. Now, of course, it's obviously much easier because you're not doing any of the work, and so there's a lot of time and a lot of effort that is not paid out from your company. However, there's going to be money paid out, and you don't have as much control because someone else is doing the work. If it's confidential material, well, they're going to have access to it if you want them to do a good job. I mean, you can try not giving them any information, but there's no guarantee that it's going to work in the end if they don't have your data to work with. And then the expertise is not in your house. It's not in-house. It's not with your company. It's with whoever made it. And so when there's issues, when there's problems, it's not something that you can necessarily easily solve yourself. You would be dealing with whoever the external firm is for that kind of thing, for troubleshooting, for bug fixes, for whatever. So it is what it is. It's business. It's either going to be, you're either going to trust the company that you work with and expect to have a relationship with them and be okay with paying them a good amount of money to do it, or not. Or you're going to do it. You're going to find a way to do it yourself. So that's outsourcing, and that's really, I'm not going to spend any more time on it than that. It's as simple as paying someone to do the work for you. So which design strategy is going to be good? What is going to work for us? Well, they have a little chart here that tries to help, giving specific things such as business need, in-house experience, and then say use these different types when this is the result. I won't really talk about it. This is in your textbook if you want to look at it. It's a good starting point, but nothing is set in stone. There's always going to be external factors that are going to color and change these decisions that you make. And so that's it. So to sum up what we talked about here, you need to make sure when you're transferring from the system analysis to the system design phase that you have all of the analysis models verified and validated. They have to be that has to be consistent and sane before you start working on design, because if it's not, your design is going to get it's just not going to be consistent and you're going to find flaws. Once you have determined that your analysis model is good, then you're going to evolve into the design model. You're going to be taking all those diagrams and use cases, and you're going to be moving them into design and into packages and into groupings to make sense for the design, for how you're actually going to be coding and creating these systems. And then you're going to determine which kind of design strategy is going to work for you. Is this something you're going to do all by yourself? Are you going to use existing software? One last thing about existing software is you don't have to even necessarily use full software. You can be using packages. You could be using additional APIs that help you with certain functionality, so you're not coding everything from the ground up. And then once you've decided on the strategy, then you develop the actual design itself. And that's going to be what we're going to talk about over the next several chapters, is actually getting the design, start looking at code and looking at how you're going to code and making decisions about that, rather than this top-down broad overview that we've been doing up until this point. So that's it. That would be it for Chapter 7. And coming up in Chapter 8, we're going to dig right into design and start figuring out how we're going to go about designing these systems. All right, have a good day, everybody.